Welcome back to Tanning Emotion and the Strengthening Numbers webinar series. My name is Peter Holmertz. I'm heading up Tanning Emotion in the United States. And I am so grateful today to invite Bjørn Harald Olstad from Norway in Oslo. You're working there at the Norwegian School of Sports Science. Doing research and all kinds of stuff and a lot of focus on swimming. So welcome to the show, Bjørn Harald.
Thank you very much, Peter. Delighted to be here. Thanks for inviting me.
No, it's great to have you on board. And so thank you so much for preparing for this and what I know will be a very interesting presentation on swimming and how to monitor or utilizing technologies for swimming performance. Before we get started, I only want to remind people that you can type in your questions. There's a little toolbar on your webinar screen where you can, you click a button there and you can then type in your questions and we will make sure those are answered. What we're gonna do is to do a separately recorded Q&A session. Just to make sure we utilize this time well, and then we're going to record that afterwards and publish it online together with the recording of your main presentation. Also, this is our last session in this series that we have scheduled and run here during the spring. We're so grateful for all the speakers that have spent a lot of time preparing. We started with Matt Price from the LA Kings in early April, and we've been running a session every week since. Now we're going to take a break for a number of reasons. Primarily is that people are starting to get busy again. The COVID-19 situation is, of course, not over by any, it's continuing and it's a serious situation for everybody. But people are starting to get back into some kind of normal. Sports are starting to happen again, and we notice that people are getting busy. So we're going to take a break with the webinars and plan some new sessions down the road, and let everybody know when that will happen and the interesting topics that we will schedule. With that, thanks again, Bjørn Harald. I'm going to let you take off now, but why don't you tell us a little bit more about your background and kind of where you're coming from before you dive in?
Thanks, Peter. Well, thank you for the kind introduction too. I'm now 46 years old, but been a competitive swimmer for most of my life, even though I started quite late as a 12-year-old. But still, it was not too bad in terms of making it to a fairly high level. I lived in the States for quite many years, came there to swim in college as my big dream. Finished my collegiate career, but didn't feel like going home, so continued to study masters and started as a swimming coach for college and club team. Then back in 2002, I was appointed by USA Swimming headquarters up in Colorado Springs and got to work with the national team in terms of performance testing and education. Very exciting times, and also at the beginning of Michael Phelps's career. And after 8 years in America, I decided to come back to Norway. And then I started to work as a performance director and a daily manager for a swim club here in Oslo. And then afterwards, I transferred over to the Norwegian School of Sports Science in 2009, where I did my PhD in swimming on muscle activation and kinematics in contemporary breaststroke swimming. And together with many of my good colleagues here, we are doing a lot of applied research in swimming with a special focus on performance.
Wow, you have an impressive background. You've seen a lot, been in a lot of places. That's
I've been fortunate.
Yeah. Thanks for that background, Bjørn Harald. I'm going to let you, move forward now with your presentation. I'm going to go offline here or off mic and video and leave you with the audience. So again, welcome everybody, and thank you, Bjørn Harald, for being here.
Thank you, and welcome everyone. So we have quite an extensive list of topics today because when our school got rehabilitated about 2 years ago, we were fortunate to acquire a lot of new state-of-the-art technology that we try to implement and into our applied swimming research. So I hope it will not be too packed, and I hope we get through most of it. And in case something is, or in case we're going over time, we will take this back in the Q&A session later. But the two main technologies we will spend the most time on is the race analysis, which is a video camera system with automatic movement recognition, and it's the velocity, force, and power, as well as drag measurements that we get from a portable winch system and a land strength system. We will go into some muscular activation with surface electromyography, and then we will try to connect the dots to daily and live monitoring and feedback then during training in terms of stroke kinematics from inertial measurement units and heart rate from optical heart rate sensors. But first, I would like to show you this slide, which comes from Professor Villas Boas in Portugal. And it's basically showing their approach to an analytic approach to swimming research. And looking at this figure, you can see that there are quite many factors that are determining for the performance. And the reason I would like to show this one is mainly because with the technology that we were able to purchase, we can now measure not all, but almost all of these different variables. So if you go to the middle of the screen into the yellow square saying race analysis, which is then considered the optimal performance test. I mean, it's the race itself, and as we know in swimming, the winner is the fastest swimmer. But in order to have a great race performance, all of these other factors play a role. So then if we go to the bottom green square, we find physiology, energetics, anthropometry, biomechanics, and motor control. Many underlying components there, we cannot measure all of them with our technology, but at least we can measure one or more. So technology gives a lot of possibilities in terms of determining and monitoring performance. So let's start with the race analysis technology. It's basically an integration between two systems. It's the AIM, Athletes in Motion, camera system, and then Swiss Timing, which provides the automatic timing from the touchpads and from the starting block. So the camera system itself has 11 cameras. 5 you will see placed above the water surface. 5 are beneath, and they are all fixed cameras 5 meters apart. And the 11th camera is also underwater at the middle of the starting lane at the starting side. So it provides you with a back and front view. We also utilize then this big sport-specific scoreboard that we have at the pool, and also a portable monitor when we are then utilizing the cameras in individual mode. And it's mostly then for students and the swimmers to swim a lap, swim a certain distance, and afterwards they can look up, and thanks to the delay function, they get to see themselves. So what do we then get from this race analysis system? So if Peter would be kind to play the video. I don't know if you guys see the video, but I guess I probably don't. All right, so I think, yeah, it's coming. Oh, here it comes. So basically what you see then is a split screen from the above and underwater cameras, and it's stitched them together, forming an almost seamless movie. In addition, on the right side, you find now the left quite some of the important stroke matrices. You find the instantaneous velocity. You will see the hip and head depth, the stroke rate, all pinpointed to the location and time for the race. And in addition, you will have the block time, the turn time, the break time, break distance, cycles, and of course the lap time. So in addition to this video, we also get the graphical representations of the race. And
sorry for interjecting. I think you have to accept become the presenter again there, so we can see your screen.
That means that it probably went out, sorry. click to start.
Yeah, now you're back.
Back.
Oh, it was back for a split second there, but it disappeared again.
Okay, sorry. Now it should be back, hopefully.
Now it's back. Thank you.
Yeah. So yeah, so here you then see the graphical representation of the race as well as numerical numbers. And as a coach and a swimmer, you get a lot of fancy data. How do you utilize it? Do you just go blind on all these numbers, or how do you start to work with it? But of course, I should also say that in addition to what we get from the system, we also use MATLAB to further programming, so we can go even deeper into the race itself when we want to look at the performance deciding factors. But basically, we used to look upon this as the normal way of doing race analysis. You take the swimming race and you break it into the free swimming part, which you call often the clean swimming. And it consists of the stroke rate and the stroke length, and the product becomes the swimming velocity. On the right side, we find what we call skills, which is the start, often defined as then 0 to 15 meters. The turn, often from 5 meters before the wall to 10 or 15 meters after, I guess depending on the stroke and the underwater distance they are traveling. And the finish, which is normally the last 5 meters. But of course, during the start, the turn, many other things will decide how fast you are. For example, the start, what is your takeoff velocity? What is your reaction time? How long do you glide? When should you start your first underwater motion? When should you break out? And similar goes for turn, also including the pivot. So we usually look upon this from 4 perspectives. And one is segment contribution, like we identify the contribution of each segment to the finishing time. It's not a very sophisticated way of looking at it, but it's always nice to go back and revisit this topic because it puts things into perspective. How much time do the swimmers spend in the different segments in a race? Here are some examples of 3 different studies that we did. We will not go into all the details in the results, and I guess I forgot to say that in the beginning. I will present quite a bit of results, but I don't think we have time to go deep into them, so I would like you to then leave Q&As if you want to hear more, or please feel free to contact me after the session with the email provided at the end. But one example is from the men's 100-meter short course breaststroke. So here we looked at the 6 best swimmers in Norway at the championship final. They came to our pool the day after for testing in the race analysis system. And what you can see, maybe not very surprising either, is that the turns compile the largest part of the race. But what I think is very interesting is when we look at the break time from starts and turns. And here it's the individual measure of the swimmer, meaning when the head breaks the surface after the start and after the turn. So it's not really related to the clean swimming at all. More than 38% of the 100-meter short course breaststroke is related to either the airborne phase or the underwater phase. So what we then like to ask the coaches and swimmers, when it's so important or contributes so much to the performance time, how much time do you actually spend on this, practicing it with 100% focus during your daily training? If you go over to the men's 50-meter short course butterfly, we see that the contribution is changing quite a bit. The blue numbers indicates that it's increasing from the 100-meter breaststroke race, and the red that it's decreasing. So of course, the start will here be more important in terms of contribution because it's only a 50-meter race. But also here, we see that the start and the turn break time contributes to almost 35% of the race. But also more interestingly here is that look at the standard deviation, which is quite large, 6.55. And again, that shows us that elite swimmers, I mean, these were swimmers also qualified for the national championship. They have quite different strategies in terms of how long they stay underwater in their underwater kicking. And we will not further go into the women's 50-meter short course front crawl, but you will have the numbers on the screen. Component contribution. And this is probably maybe the most interesting part in that sense, because which segments and the components in these segments are determining the performance. So again, going back to the men's 100-meter breaststroke study, we found a nearly perfect correlation for the 15-meter start time with the finishing time. And saying this very simplistically, this means that the swimmer that was number 1, 2, and 3 after the start was also the swimmer that was 1, 2, and 3 at the finish, meaning they could have stopped the race, given out the medals, and the race would have been over. Of course, in real life, it's not that simple because we have to swim the race and things can happen. But what this shows us is that what the other swimmers lost during the start, they were never able to require after the start. So then we were curious, what part of the start is crucial? So then we broke the start into 5-meter segments, the first 5, the middle 5, and the last 5 meters of the start. And here you can see that the last 5 meters, the 10 to 15 meter mark, showed a nearly perfect correlation together with the starting time. So then it's important to go further into that part of the starting segment. What constitutes the important factor there? And here we found that the peak velocity showed a very large correlation with the 10 to 15 meter time. And also we see here that the peak velocity has a range of from about 2 meters to 2.5 meters per second. And this is then generated from the underwater arm pull, which then appears to be the crucial part of the start. How high peak velocity do you actually get from your arm pull? And it can of course be related to, are you gliding too much before? Do you generate velocity from your underwater dolphin kick? Or are you simply not strong enough or have good enough arm pull technique to generate this high velocity? We did the same thing in the 50-meter short course butterfly, where we also looked at start and turn performance. And maybe not surprisingly, the mean underwater kick velocity has a large impact on the 15-meter start and the 10-meter turn time. And again, since butterfly has the rule that you can kick 15 meters underwater, most of that part will anyway be underwater. But we can see that for the start, it had a negative 0.689 correlation, but almost a perfect correlation for the turn. But what was interesting here is what comes in red, that this was regardless of the initial velocity, meaning that the velocity that the swimmers entered the water from the start or from the push-off during the turn had no influence on this mean kicking velocity. At the same time too, the velocity deceleration from the underwater kicking did also not have an influence on the underwater kick velocity. And I mean, expecting that having a high peak velocity going off the wall and off the block is important, it was kind of surprising. And if you look at the first kick velocity, it appears that this one is essential for the mean underwater kick during the start. So what this means is that the fast swimmers are starting their first underwater dolphin kick with a higher velocity than the others. And this can be related to the body angle when they enters the water. Like some swimmers might have a pretty steep angle traveling a bit downwards before they are flattening out to have their horizontal body position. And of course, others might glide too long. But to start the first kick with high velocity is important for a good start. But in the turn contradictory, well, not contradictory, but oppositely, here the last kick velocity showed to be very important. And again, when you push off in a turn, you are almost more or less horizontal. So you don't need to be so good in manipulating your body angle. So here it's much more the underwater kicking technique itself to then maintain the high velocity and come up with the breakout on a high last kick velocity. And then one last example of this, because I think this is very interesting, and it's not coming from our race analysis system, but it shows how important this is for performance. This comes from the World Championship in 2018, and not much race analysis has been done on the long distance event. So this was done on the first, second, third, and sixth place finisher in the men's 1500 meter front crawl. And if you look at the figure, and towards the bottom, you have some red and blue numbers. we see here that the winner of the race, the first place finisher, had a total turn time of 295 seconds and a total swim time of 553 seconds. And what's very interesting here is that you see the second place finisher. This person swam about 4 seconds faster than the winner of the race, but the turn time was 5 seconds slower, meaning that this person lost the gold because of a slower turn time. And also to make it precise, the turn here is classified as 5 meters in and 5 meters out. Even more interestingly is when we look towards the right for the third place finisher and the sixth place finisher. Here we see that the sixth place finisher swam roughly 7 seconds faster than the bronze medalist. But this swimmer lost actually almost 15 seconds on the turn, leaving this swimmer in sixth place, while the other swimmer got third place thanks to an excellent turning performance, which is almost identical to the winner of the race. So this is just an important perspective in terms of why race analysis is important for performance. Another way of utilizing race analysis is to use race modeling, which I think is a very practical and applied way of using it. So here you can compare yourself to the gold standards, you can compare yourself to others and to yourself. So again, going back to the 100-meter breaststroke study, we did a race modeling. On top, you will see the fastest swimmer in this study, and below you will find the fastest time. So regardless of which swimmer had the fastest time, that's what it's plotted against. So when you see that the fastest swimmer has a green box, then the swimmer was within 0.099 seconds of the fastest swimmer, meaning the swimmer is good at this. Yellow between 0.1 to 0.199 seconds, and we classified red if the fastest swimmer was more than 0.2 seconds slower than the fastest swimmer. And we can see that the fastest swimmer is quite good in many of the aspects of the race. But one particular parameter, this swimmer scores quite poorly, and that is the pivot time. And in breaststroke, we give pivot time from when the hand touches the wall until the feet touches the wall. So by looking at the time that this swimmer spent here, this swimmer could have swum almost 1 second faster if he was also the best at the pivot time. So it's quite something to think about. So it's important to use race modeling in that sense to see where are you scoring well and where are your main factors for improving performance. And one last way we can use race analysis is to compare yourself after training. So basically you come to the test, you get your race analysis, you identified some parameters you need to work on, and then you go back and do it. So in this example from 50-meter front crawl, we have the left and right stroke distance. And when this swimmer came to the initial testing, we see that the average distance from the left arm was slightly above 1 meter. Looking at the right arm, it's below 1 meter. It's quite a difference between these two. So then the swimmer went home to practice their distance per stroke on the right arm in terms of improving it. Later they came back for testing, and here we see they're almost equal, both more than 1 meter per stroke, or per arm, sorry. Again, leading the swimmer to swim with a longer stroke distance. Some future perspectives or directions that we would like to go in terms of race analysis is to look even more into start and turns, and from the perspective of how to optimize the underwater work. When should you time the dolphin kick? How do you time then the dolphin kick to the arm and leg motion in breaststroke? The velocity fluctuations, the decline, and what is the ideal breakout point? What should your velocity be compared to your swimming velocity when you break out from your underwater work in the 4 competitive strokes? We would like to implement the inertial measurement units because then we could get even more detailed stroke analysis. And of course, it would be nice to do some intervention studies in terms of effect of training on race analysis parameters and performance. And also it would be very nice if we could include force measurements in the starting block and the turning plate to see how the forces are distributed throughout the start and the turn. And that takes us over to the next topic, inertial measurement units and IMUs. We will not go into detail in terms of what an IMU is, but on the right side here, you see the IMUs that we collected throughout this process. And you can see it's a very small and light IMU, weighing roughly 5 grams, and also with very small dimensions. But of course, swimming is in the water, and we have many challenges with technology in the water. Here we have something that we need to be aware of when using IMUs in the pool. And again, we will not go into the details about this. You can go to the references if you want to read more. But I guess one big challenge is usually how you seal the sensors. How do you keep them waterproof? Luckily enough, the sensors we have are waterproof, so we don't have to worry about that. But again, there is still no consensus yet in the swimming world about where should we place these IMUs for collecting the different types of data we want. And of course, in swimming, when you have the drag from the water, it's quite different than doing on-land exercises. So of course, if these IMUs are significantly in size and weight, they will impose a drag on the swimmer. And of course, again, the feel for the water might be altered depending on where you place them. And of course, again, the size too. But if you look at the commercial market today, you find many of these so-called IMUs, or at least included in technologies like sport watches or other ones that can track quite a bit of stroke metrics. On the left side here, you see a system called Triton, and it's the one that claims today to be the most accurate. And if you look at some of the validity measurements from this system, this was then compared to video recordings, you see that the system is very good in terms of coefficient of variance being lower than 5 or 6 for split time, speed, stroke count, and stroke rate. But on the other hand, when you look at distance per stroke, the time the swimmer was underwater, and turn times, it's quite a high coefficient of variance. So in that sense, IMUs are starting to become available. They're also starting to be more and more accurate. Again, depending on the purpose, can they be utilized or not? Here's an example of a collaboration we did with some researchers in Portugal, and it kind of shows the possibility or the future possibility of using IMUs, because here we were trying then to develop or create algorithms to detect more stroke kinematics besides what we would get from the video capture, at least in 2D. And here we have then the body rotation, which we know is quite important in especially front crawl and backstroke. Like how much does the body rotate in the longitudinal axis? On the other hand, too, you can have excessive rotation and of course asymmetrical rotation. And of course, in breaststroke and butterfly, you want this rotation to be minimal, more or less at 0. Trunk elevation, on the other hand, is interesting in terms of butterfly and breaststroke when you're looking at the undulation technique, meaning how much body undulation do you see in the stroke? And if you look at especially breaststroke over the last decades, it has gone through many changes from first being a very flat stroke, then a very undulating stroke, and now breaststroke is still undulating, but more towards the flat. And also in butterfly, I mean, we want to move as quickly as possible horizontally. So again, excessive up and down movements will slow the swimmer down. And finally, we were also looking at the body balance, or what we call pitch angle. And again, we know that in front crawl and backstroke, we should be as horizontal as possible to have minimized drag. And of course, if this angle increases and the legs are going down, the drag will increase. So here's just a way of how to utilize IMUs. Down to the right, you see a movie from Triton, and they have placed their sensor on the back of the head. Down to the left, you see me trying our IMUs for the first time doing butterfly. But when it comes to IMUs, I think it's the missing piece to swim coaching, because it's the way of providing instantaneous feedback on stroke metrics to the coach and to the swimmer. As you can now see in the movie down to the right, you can have the live streaming out to an iPad or to a monitor in the pool. Because for everyone who has coached swimming, having 15, 20 swimmers in the pool at the same time, it's quite complicated to follow each one in a very detailed manner. Many coaches are left with a stopwatch providing split times, the occasional stroke technical feedback. Of course, swimmers can count their own strokes, but it's very limited how much you can get out of it. So of course, if something could track the swimmer's daily training and then continuously monitoring this data over long periods, you will get a great tool to see, first and foremost, are you improving on the parameters that you want to improve? And also in other cases, you want to be better in underwater kicking. The coach and the swimmer has an agreement. You should do 6 underwater kicks after each turn. The swimmer is a little bit tired today, so they cheat on the opposite side of the pool when the coach can't see it, doing only 3 or 4 kicks. Then of course, if you had this IMU or live tracking this, the coach can say, hey, you're only doing 4 kicks today. Why? So basically the point is, I think we have a lot more to offer in terms of stroke technique and improvements by having this continuous data. And I don't think we are quite there yet, but I think we are moving quite rapidly forward in terms of being able to utilize these IMUs in a full possible way. So what I think would be interesting in this case is for us to then integrate this with race analysis, and then we could acquire additional parameters such as the body roll and the undulation. You can look at the pitch angle, and also you can then divide the arm stroke and the leg kick into different phases to see actually what is occurring during these phases when you swim. Of course, instantaneous velocity is a very nice parameter. From race analysis we have it, but not from the daily training, because I mean it is the best estimating of swimming performance. And if you have very large velocity variations when you're swimming, there are things in your technique that you have to go and investigate. And of course, what would also be interesting is then if you can take the IMUs to combine joint angles. I mean, today it's very tedious and laborious. Of course, with 3D kinematics and automatic tracking, it's quite doable, but not from the normal 2D and the normal video recordings that we see. So in that sense, we could then go into the arm stroke phases, the inter-arm coordination, and of course, intersegmental elbow and knee angles, cycle per cycle. And of course, then you can see how consistent is the swimmer cycle per cycle. Do they have an optimized automatic stroke pattern, or do they have a lot of stroke-to-stroke variability? Strength and power, land and water technology. So to the left, you see the 1080 quantum, and on the right side, you see the 1080 sprint. Two technologies that we also acquired during this rehabilitation process. And why is this interesting for us? Well, one reason you see right here, the swimmers have changed through the last 100 years. I mean, looking at Tarzan to the left, Mark Spitz in the middle, and then to the modern swimmer, it's clear that they are now much more powerful and they're physically stronger than ever before. And also when we look at the way swimmers train today, compared to like, for example, in the 80s, many things have changed. I mean, back in the 80s, the purpose of the land training was to build strength endurance. That was the crucial part. And if you look at the highlights in red, you see that 1 repetition maximum with unspecific velocity, not meaningful. And also there are low maximal strength requirements in swimming. Looking at today's strength training, now it's development of maximal strength that is the basic. And you use methods with high to very high loads. And I think this quote from Adam Peaty summarizes it quite well. A swimmer's physique is built in the gym, not in the pool. So then we were curious, what are then the requirements for strength in swimming? So we went to the Norwegian Swimming Federation and our Olympic government. And the only parameter that we have classified in Norway as important is the squat jump, meaning squat jump is important for the start and turn performance. So they gave some recommendations in terms of how high you should jump in squat jump in terms of reaching the Olympic Games final for men and women in the different strokes and distances. But we think that there's more to it than just squat jumping. So we went out to look what else is out there. And then we found that the British swimming have classified 3 other exercises as important if you want to be an elite senior swimmer. So they identify that chin-ups, and then they provided how heavy you should be able to lift up, body weight plus additional kilos. They used bench press and back squat. And then they classify that for female, sprint, middle, and distance. So then how can we utilize then this technology? So I think the topic of force velocity, load velocity has been covered quite well in the other webinars, so we will not go into too much detail about or the specifics about it, but we will talk about it from a swimming perspective. So basically what you can do then by generating a load velocity profile is that, for example, you can see if a swimmer is load or force dominant, if they are velocity dominant, and what are their production capabilities. So we were kind of interested to see, can we see some parameters from a load velocity profile in dry land strength exercises that could be important for the swimming performance? So we have only done one experiment so far where we used the 1080 quantum, and there we had the butterfly swimmers perform a load velocity profile in leg squat and in bench press. Unfortunately, we could not find any variables from the load velocity profile correlating with the 50-meter butterfly performance, but we found that squat jump, as identified previously, had a high correlation with the performance in the start and turn segment. It doesn't mean that we cannot find important findings from land exercises, but from these two, perhaps they were too unswimming specific, or it could also be other reasons for it. So therefore, we kind of moved more over to the pool. And here we utilized the 1080 sprint machine. And basically what you see here is our experimental setup for semi-tethered swimming. And when we talk about semi-tethered swimming, you will see that the swimmer has a belt around their waist, and then it's connected to the wire going out of the sprint machine, which again is placed on the top of the starting block. So it's 1 meter above the water surface. And then we use this to predict and assess swimming performance. So over on the right side here, you will then see an example of the load velocity profile that we generate in swimming. So here you see the different marks, 1 kilo, 5 kilo, and 9 kilos load. So that means that when we are testing the swimmer, they are swimming 25 meters with maximal effort. And on the first trial, we give them 1 kilo's resistance. The second trial, the 5 kilos, and then 9 kilos resistance. And then we collect the data from the 5 meter to the 20.5 meter mark. And then we plot it into and get the regression line and the load velocity profile. So basically what you will see here is that the LO, that's the predicted maximum load that the swimmer could pull, and VO is the predicted maximum velocity. So before using a performance test, it's important to know if it's reliable or not. And what you see here now is some preliminary data from a study that we conducted in terms of reliability. And on the left side, you will have again the LO, predicted maximal load. You have the RLO, which is then the LO relative to body mass of the swimmer. You have VO, predicted maximum velocity, slope, and then you have the adjusted R squared, which is basically how well the measurements are fitting the regression line. So if you look at then the coefficient of variance, almost every parameter is under 5%. And I'm sorry, I forgot to tell you what, again, if you look at the table, you see the load velocity profiling when we did 5 different loads. Here we tested the swimmer at 1, 3, 5, 7, and 9 kilos. And on the bottom, you see the same calculation, only using 3 different loads. It's based on the same data, but here we excluded the 3 and the 7 kilos measurements. And as you can see, it's very similar, almost identical, between using 5 and 3 different loads for calculating load velocity in front crawl swimming. And again, looking at the reliability results, you see that the interclass correlation coefficient also have excellent values. Almost every measurement is over a 0.9. And moving over to the right, we see SEM, which is then the standard error of the measurement. And on the right of that again, we have the minimal detectable change. You should be quite careful in using this minimal detectable change from this table in terms of using it for predicting performance changes, because in this study, there was boys, girls, men, women, different performance levels. And of course, if you have 2.8 kilos as a minimal detectable change to see an improvement in performance for LO, and you as a swimmer can only pull 8 kilos, which was the case here, it's quite a large improvement you need to make. On the other hand, we had male swimmers pulling 23 kilos. For them, it would be much less. But the reason why I'm showing it is because you see that the MDC is quite larger than the SEM, which is a good thing in terms of reliability, because then the standard error of the measurement is classified as low versus the possibility of seeing actually a change in performance. We also use this to predict performance, meaning here you can see 50-meter butterfly swimmers. And on the x-axis, you have VO, which again is the predicted maximal velocity from the load velocity profile. And on the y-axis, you have the Vmax, which is actually their swimming velocity from a 50-meter butterfly race. So in this setup, we first tested the swimmers in 50-meter butterfly all out in the race analysis system, and thereafter they provided a load velocity profile. And what you can see here is that then the relationship between the predicted maximum speed from load velocity and the maximum swimming speed during 50-meter swimming has a very large correlation, and also a very high intra-class correlation. So basically what that means is that the velocity predicted from load velocity corresponds very well with the actual swimming velocity during a race. So again, if you have a minimal detectable change in your velocity outcome from load velocity, that should also then transfer into improving your swimming velocity. Here you actually see a mix of 3 different studies that we did. And here we tried to look at the parameters coming from the load velocity profile and link it towards performance measurements in the swimming race. So on top here, you see then the V50FC and the V50BF, which is then the velocity from swimming 50-meter front crawl and the velocity from swimming 50-meter butterfly. And again, we see strong relationships between the velocity that you make during your race to how strong you are, meaning how high your LO is. And if you look at the 50-meter front crawl study, you will see that this is even higher when you relate it to percentage of body weight. So when LO is related to percentage of body weight, it has even a higher correlation, significant importance for the performance. On the bottom here, we have a study where we used girls age 11, 13, and 16, and we didn't measure them in a 50-meter race, but we measured them in a load velocity profile. And basically, here we have the predicted maximum velocity from the load velocity profile in FC front crawl, BA is backstroke, BR breaststroke, and BF butterfly, so in all 4 strokes. And here we looked at it in relation to percentage of body weight. And interestingly here is that if you look at the front crawl and backstroke, there is a significant relationship between their predicted velocity max and their predicted LO in relation to body weight. But this is absent in both breaststroke and butterfly. So what this points towards is that the alternating strokes of backstroke and front crawl, it is important to be strong and generate high propulsive forces to get a high velocity, while in breaststroke and butterfly, in these age groups, this might not be the deciding factor. Here it could be much more related to how do you minimize the drag and how is your stroke technique. And here we have an example again from the load velocity profile of the 50-meter butterfly swimmers. And here you see all the swimmers' profile in the study. And if you go back to the slide before, when we see that there's a stronger correlation when you take the predicted maximum load and relate it to the percentage of body weight, It would probably have been more interesting to look at this also for this study, but unfortunately here you only see the actual true values. So what's interesting here is if you look at the blue line, that swimmer is extremely strong. And it's also the second fastest swimmer in this study. The swimmer in red is also strong, but not close to as strong as the blue one, but it's the fastest swimmer in the study. Both of these swimmers are international top level or international level swimmers. And they're also extremely different in terms of their physique. So if you wanted to give some recommendations to these swimmers, what would you do? Well, probably first and foremost, we would relate it to the body weight, because we know that the blue swimmer is much taller, it's much more heavier and muscular than, for example, the blue swimmer. But at least from analyzing this, we could say that the swimmer in blue is extremely strong, perhaps even too strong, because we know that added body mass from muscles also increases or can have a good impact on the drag, because your body will be heavier in the water. And also, it's not really able to utilize all of this force to kind of generate high velocity. So at least to put the swimmer on more explosive strength or swim training could be beneficial in order to improve their maximum predicted velocity. For the red swimmer, was quite a steep slope. Again, swimming the fastest, which is the main output anyway. How could this swimmer then improve their performance? Most likely by probably increasing a little bit of their maximum strength possibilities, and again, probably improving on their peak power output. And this takes us over then to the peak power training, which is very popular in many sports. And I just read from rowing some time back that rowing claims that the peak power is the #1 deciding factor to rowing performance, together with the rowing technique. Much more important than, for example, VO2 max or lactate threshold. And then what is the case in swimming? Is it important to train and develop your peak power? Is it important to practice resistive training, specifically in the water? At least if you look towards the right figure here, we see one male breaststroker that we tested. And in the red line, it's the load velocity profile, and the blue, it's the power curve. And basically, if you look then towards the top of the screen here, we see that this swimmer's LO is almost 23 kilos, so quite a strong swimmer. The Vmax is 1.53 meters per second. So going to the theory behind load velocity and peak power, we see the L optimum is classified as 11.45 kilos, and that is the load corresponding to where the Vmax velocity has decreased 50%. And in the V optimal, that's the velocity where this occurs. Further on, we see this L deceleration 10%. That is the load corresponding to a 10% decrease in the velocity max. And the V deceleration 10% is that actual velocity. So far, I only know about one study who tried to do an intervention using resistive sprint training with the 1080 sprint, coming out of Sweden, testing their elite swimmers, elite sprint freestylers. They were using the L deceleration 10% as the resistive training, which for this breaststroke would have been 2.29 kilos. But after 6 weeks of intervention, together with a control group, they couldn't find any significant differences in the velocity. Of course, they saw individual differences. Some swimmers actually had quite large improvements in the experimental group, but not as a group. And one challenge that they mentioned from that study was that there were swimmers from different clubs, and they were not able to control what they did outside of the pool, for example, in terms of land strength training, how much they actually swam, and what they did besides the experiment. And also one theory in swimming is that if you were to train at L optimum, which would decrease your velocity by 50%, it would perhaps alter your stroke technique too much in terms of being beneficial. But these are still questions that we don't know too much about yet. But at least the purpose about generating this power curve, at least that you could then choose and pick which spot you would like to do, and then programming the 1080 sprint to let you train at that certain resistance or with that velocity. So again, how to utilize this technology. Here again, we see the power curve from stroke to stroke cycles in breaststroke girls. And from the top swimmer, you see that it's a very flat mean power curve, indicating that this swimmer is very good in keeping her power cycle by cycle throughout the test, both at 1 kilos load, which is the blue, and at the heaviest load she tested, the kind of orange, 5 kilos. Swimmer on the bottom, on the other hand, you can see that her mean power is decreasing throughout the swim. This means that even at 1 kilo, the swimmer is not able to keep up her power. So this swimmer might have a challenge in actually generating good high power in her swimming, and even more so to maintain it, either due to fatigue or also possible to stroke technique and the drag. But at least this graph here will show us if the swimmer is good in generating high power and how well they can keep it throughout the distance. Just a quick example in terms of breathing and asymmetries that we did from a little student experiment. So if you're looking towards the right here, you see the distance and the force, and the green is when the swimmer did no breathing, blue is breathing right, and red is breathing left. And I mean, as a coach, you keep telling your swimmers when you sprint freestyle, you should not breathe. And this is quite a visual representation of why you shouldn't, because here you can see that the force production is much higher when you don't breathe. But of course, also looking at this, you could then identify, does the swimmer have any asymmetries between breathing to one side or the other? Do they have a preferred side, a weaker side? Should they then spend time on improving the weaker side? Or is it even better just to actually go for the strong side? And finally, what we are now starting to experiment with is then the passive drag. I mean, we know that from the start and the turn, you have not a significant large amount of time, but there is some time when you're spending in streamline. And how should your body position be in order to minimize the drag and maintaining the velocity? So just quickly here, some future directions. We want to then try to establish relationships between load velocity parameters and swimming performance in all the different strokes. We have quite an extensive database right now, so I think we will soon start to go deeper into the other strokes, different genders, different age groups. The second question here would be very interesting. Is there an optimal load velocity relationship for different strokes and distances? Would it be possible to identify what is the optimal profile? Could we also look into lower and upper body contribution in terms of the stroke technique? And of course, a big dream would be to look into active drag. Then we are moving over to heart rate in swimming. And here we see some different devices in terms of measuring heart rate. And if I'm not mistaken, I think the first device, at least portable, came from Polar in 1977. And since then, the technology has improved quite significantly. And for most people involved in endurance sports, at least in Norway, when you think about running, cross-country skiing, many use heart rate as a tool for measuring intensity. While in swimming, this has been very little utilized, up until now at least. So one question is, of course, how accurate is heart rate or optical heart rate? We know from previous validity studies that the Polar H10 chest belt is very valid compared to ECG. But we know very little in terms of optical heart rates. We know that in the past it has been not very reliable and valid for measuring heart rate in swimming, but also in other activities and sports. Here you just see an example of a figure from one of the testings we did when you see the H10, the OH1, and the M600 throughout the training session. And as you can see here, the H10 and the OH1 optical heart rate sensor are following each other very well. If you look at the picture to the left, that's me in my triathlon suit in an early pilot stage of this experiment. Here we place the chest belt around the chest, and the OH1 sensor is here placed on the temple of the head underneath the swimming cap. And it's also very important not to make sure that there is no hair coming underneath it. So the big question is, how accurate is optical heart rate? So this is some data from a recent paper that we published. And if you look at the H10, which is then the criterion measurement, and in this study we used both male and female swimmers, and the chest belt was then placed underneath the swimsuit. And that's mainly because the chest belt for male swimmers is not very practical, because every time you push off from a turn, it will slide down. So what we see here is that the H10 and the OH1 has no difference. Well, on the other hand, M600 in terms of heart rate max and heart rate mean is significantly lower than the H10. And also again, the ICC values are very strong for the H10 with OH1. But also maybe what's more important is it also able to identify the different training zones or the different intensity zones? So again, we look at the heart rate zones to the left, under 50%, 50 to 60, and so on, up to 100%. We use H10 as the criterion measurement, and then we have OH1 in blue and M600 in red. And again, there is no significant difference between the H10 and the OH1. Well, again, the M600 for certain heart rate zones tend to be lower and also higher than the H10. So basically what we can take from this is that OH1 is an accurate measurement of a heart rate in the water during swimming, while M600 is placed on the wrist is not as accurate. So in that sense, the question is, how should you then utilize heart rate in swimming? I mean, swimming is extremely velocity dominated. We can basically use velocities or time for distance to predict what intensity the swimmer should hold. And in that sense, we could use VO2 max, which is very complicated to do in the water, so we don't do that very often. That's more for land-based activities. But we often do lactate in terms of step test or critical swim speed tests. Heart rate could be used in terms of percentage of max heart rate, and of course RPE can be used as a subjective measurement. But again, the point is that in swimming we are usually mostly using velocity or time. So let's say today the swimmers are doing 10 times 100 freestyle, corresponding to 110 per 100 meter, and that should be intensity zone 3. But we also know that training adaptations make differences to how fast we should swim. It also depends on our daily shape. Like I became dad 4 months ago for the second time, and I must admit my sleep is not extremely good all the time. So of course, if you're sleeping bad for one night, consecutive nights, you have a lot of stress, your body will not get the same impact swimming 110 for 100 meter freestyle. It might get a larger impact because your body is fatigued. And of course, if you keep doing that day after day for a long time, you might even end up in overreaching and, in worst case, an overtraining state of mind. So the purpose here of introducing heart rate is that it would be an objective measurement of your intensity or the effort level that you put in, that, as you can see in this movie, can be recorded live onto an iPad. So the coach could be on the pool deck telling or showing the swimmers, okay, hey, you are training in the right zone today, great. You are training too slow, too fast. It would be a way of monitoring and correcting the intensity in an objective manner. And I think I see time is running very quickly, so I will just quickly go to 2 more slides, and then I think we have to maybe cut. And that's basically, if you are to utilize heart rate in swimming, we need to kind of base it on something, and then it's the maximal heart rate. So we did one study that looked at different protocols to achieve maximal heart rate in sprinters and middle distance swimmers to see if there's a difference in terms of, is there a favorable set for a sprinter or a middle distance swimmer? So here we used then 3 protocols. One was step test 50 meter, 100 meter, and a 200 meter protocol, as you can see to the right on the screen here. So we wanted to first determine, is there a different protocol suited for different type of swimmers? And also again, to look at the topic of, is the maximal heart rate the same during swimming as it is during running or cycling? So just quickly go to the results here. There were no difference in the protocols between the 50, 100, and 200 meter. The mean max heart rate was the same. There were also no differences in the max heart rate between sprinters and middle distance for swimming protocols. So basically, You could either use the 50, 100, and 200 meters for sprinters and middle distance swimmers. It would more probably be a preference of the swimmer, what they would do. But what's important to notice here, and it's also what we saw back in the 70s when this topic was previously investigated, that the maximal heart rate is lower in the water compared to on land during running and cycling. So as you can see here, it was about 6.7 up to 5.3 standard deviation difference between land and water. And this basically means that it's important in that sense to do sport-specific tests if you want to utilize heart rate based on max heart rate than, for example, in swimming. And also, like if you're a triathlete, you're training running, cycling, and swimming, if you then use the same heart rate as you have for running when you go to the pool, you're quite likely to be training in the wrong intensities. So I don't know, Peter, should we maybe wrap it up and then do this for next round? Or should I quickly do some slides?
People are still hanging on here, so why don't you just do go through the EMG stuff there?
Yeah, I'll make it in 5 minutes.
Do that in a few minutes. Yeah, and then because a lot of people are interested here, so yeah. Please continue.
Thanks. I'm sorry for rushing through the end here, but time is of course ticking. So basically here on the right side in this movie, you see the testing during my PhD project, and you can see that the EMG system that we then used, also in the middle picture, when they have to use the logger and the phone up in the swimming cap, is quite different than the new technology we acquired, which is on the left side. Again, very small sensors, no need to have a receiver and a data logger present with the swimmer, stored in the internal memory. And also what you see in this movie is that we also used an Qualisys for 3D motion capture during this study. That was actually, I think, one of the first times Qualisys was used in the water, and it would be nice to bring it back for future data collection. Basically, I'm not going to give you all of these results either, but I thought I'd show it to you. But this is basically the main outcome from my PhD. And it's basically to show you what you can get from using EMG or electromyography in terms of measuring muscle activation during swimming. So in this PhD, we were fortunate to have 4 world-class swimmers present. 2 was world champions, 1 was Olympic medalist, and 1 was European medalist. So they were in our world-class group, and then we had a national elite group with the swimmers qualified for national championship, and then we also had age group swimmers. But basically what you see on the screen here now is the recommendations that you can get from using EMGs to look at muscular activation and kinematics to evaluate breaststroke technique. So basically what we see here is that the best swimmers in the world, they have, for example, an earlier activation in the biceps femoris during the leg recovery of breaststroke. And that's basically to decrease the time they spend in this phase. They activate it earlier so they can have a quicker leg recovery. And we also see in tibialis anterior that they have a later and quicker activation, meaning that, again, to reduce the drag, they are not making a premature dorsiflexion before they come up, but they bring their heels up, and then there is a quick activation in tibialis. Here it's there's some other ways to utilize the EMG in that sense. You can see if the muscle is active or not. Is the muscle resting during the gliding phases of the stroke, or is the muscle still active, using energy, getting fatigued? So in this figure, you basically see the 4 muscles on the upper body that we collected data from. It's the tibialis brachii, biceps brachii, trapezius, and the pectoralis major. And the red line here is at 100% effort, the green at 80%, and the blue at 60% effort. And we use this mainly to see if the muscle activation pattern changed with the different intensities. But here we can, for example, also look at it in terms of if the muscle is active or not by looking at the stapled black line across the figures. If the muscle is underneath this threshold level, it's relaxing, or at least it's not considered to be active. But as soon as it goes up, it shows that it's active. And then the question is for coaches, swimmers, scientists to interpret that, what is the beneficial way of activating, deactivating the muscle? And of course, you can also look here at the peak amplitude in terms of seeing how active is the muscle. And of course, you can also look at then the co-activation, for example, then between the triceps brachii and the biceps brachii. How much is the muscles co-activating during the stroke cycle? This is also an example of what we collected data from, but we have not done so much about it yet. But this is in terms of looking at the muscular correspondence between maximal effort swimming and different technique and drill exercises. And for everyone familiar with swimming, we know that swimming is probably the sport in the world who does the most drill exercises. A lot of the things we do in the pool is drills and technique exercises. But basically, just a quick example of what we then can see. In this square here now, you see that this solid line is 80% effort doing 2 kicks to 1 pull exercise. The stapled line is 60% effort, and the dotted line is 100% effort. And we know that in sprint breaststroke, we want to activate the pectoralis brachii and the biceps brachii early during the leg glide to not have an excessive glide and to generate propulsion from the arm pull. So basically what we see here is that if you perform this drill exercise, 2 kicks to 1 pull at 60%, you have a delay in the muscular activation. But if you perform it at 80%, you will actually have the same or even an improved earliness. You would be earlier even in generating activation and propulsion from the muscles. And also at the same time, if you look over on the right side where we have the muscles on the lower body, here again we have in green, it's the biceps femoris like we talked about earlier. And you can see here at 80%, the activation is even earlier than it is at 100%, but also here at 60%, it's earlier. So again, here both exercises could be utilized in order to improve the timing, or at least to make the activation in the biceps femoris earlier during the leg recovery in order to improve to decrease the time you spend there. And I think we skip this. So basically, to sum up the last slide here, some future directions in terms of EMG is that, yeah, you can look at the intermuscular coordination and connect it to the movement economy of the swimming strokes. It would be very interesting to go further into the muscular activation in different Paralympic swimmers and different classifications. Muscular fatigue during middle distance and long distance events. We also did maximal swimming with these swimmers in my PhD over consecutive times in order to fatigue them. And one thing that would be very interesting to look at from the data is, can you see if a muscle is fatiguing earlier than other muscles? And could you then train this muscle in some particular way to kind of delay the onset of fatigue and then to improve the performance? And of course, by using sensors on both sides of the body, you can again detect if there is muscular differences and asymmetries between the sides of the body. And the final slide, it's basically about future technologies. So our biggest dream is to get an instrumented starting block and turning plate so we can look at the force measurements during the start and turn. We would like to go and play with the pressure sensors in terms of measuring the forces during the swimming stroke. We would love to get Qualisys 3D motion analysis back in the pool. Oxygen consumption is something that we are looking into, and pacing lane lines is something that we are borrowing at the moment together with some collaborators in France. Thank you.
Thank you so much, Bjørn Harald. That was a very, very good presentation. And from the feedback we're getting here, everybody agrees with that. Thank you so much. And there's one question here. One asks is, will there be a full recording of this webinar be made available? And the answer is yes. We're going to publish this probably tomorrow, maybe tonight, US time, possibly tomorrow. And we'll do also a recorded Q&A session with Bjørn Harald that we'll post separately. And that's on the 10A Motion website. There's a banner there on the front on the website for our webinars. You just click in there to view this session and the previous ones that we have put out there. It's about, I think it's 9 or 10 sessions in total. really good stuff. I cannot recommend it enough to go back and view it. So thanks so much, Bjørn Harald. Great having you, finish this series, and congratulations to your new baby there.
Thank you.
I wish you a great, nice Norwegian magic summer coming up. I know what those are like. It's just the best place in the world to be in during the summer months. And thank you to all the viewers who've been watching us, maybe just this session or all of them. We really appreciate your interest, and we are, of course, looking forward to hearing back from everybody. Questions, anything here. We are in the United States and Europe. We have people, so let us know. Just look up Tenny Emotional website or social media and get in touch with us. So thanks again. I really enjoyed it, and everybody be safe out there. Thanks.
Thanks. Take care.